It looks like a foreign language written by a very angry robot. But here's the secret. x86-64 assembly is not complicated. It's just repetitive. There are maybe 20 instructions you'll see 90% of the time, and once you know the pattern, you can read any disassembled function without panic. That's what we're doing in the next 10 minutes. Every program you write, whether it's Python, C, or Rust, eventually becomes something the CPU can execute directly. Machine code, pure numbers, zeros and ones. Assembly is just the human-readable version of those numbers. One line of assembly per instruction. So the pipeline looks like this. You write source code, a compiler translates it into assembly, an assembler turns that into machine code. And a disassembler, tools like objdump or a debugger, does the reverse. It takes machine code and turns it back into readable assembly so a human can follow along. When you're staring at disassembled code, you're looking at the compiler's translation of someone's C or C++, seen from the CPU's point of view. Let's look at one line. Every x86-64 instruction has the same shape. An opcode, that's the verb, the action to take, and then one or more operands, the nouns, what the action happens to. Here, MOV is the opcode. It means move a value, and x and the memory reference are the two operands. In Intel syntax, which is what we're using because it reads left to right, the destination comes first, then the source. So this line means, take whatever is at that memory address and copy it into x. Not move it, copy it. The original stays exactly where it was. Registers are the CPU's scratch pad, tiny storage slots built directly into the processor, way faster than RAM. On x86-64, there are 16 general-purpose registers. RAX, RBX, RCX, RDX, RSI, RD, RBP, RSP, and R8 through R15. Each one is 64 bits wide. But here's the part that confuses people. You'll also see EX, AX, and AL in disassembly, and those are not different registers. They're the same physical register, just viewed at different sizes. RAX is the full 64 bits. EX is the bottom 32 bits of that same register. AX is the bottom 16. AL is the bottom 8. Think of it like nested boxes. Writing to EX zeroes out the top half of RAX. Writing to AL only touches one byte and leaves the rest alone. Once you see that hierarchy, half of the confusing letter combinations in disassembly just click into place. A couple of registers also have fixed jobs. RSP is the stack pointer. It always points at the top of the current stack frame. And RBP is the base pointer. It anchors the bottom of the current function's local variables. Now, the square brackets. In Intel syntax, square brackets mean go to memory at this address, the same way a pointer to reference works in C. So RBP-4 inside brackets is not the number RBP-4. It's the address 4 bytes below, wherever RBP is pointing, and the brackets say read what's stored there. You'll also see the word PTR, short for pointer, paired with a size. Byte PTR, word PTR, dword PTR, chord PTR. That's the assembler telling you how many bytes to read or write at that address. 1, 2, 4, or 8. It's disambiguation, nothing more. One instruction looks like memory access, but isn't. LEA, load effective address. LEA RAX, RBP-4, does not read memory at all. It calculates the address itself and puts that address into RAX. It's arithmetic in disguise. Compilers use LEA constantly for simple math because it's a single, fast instruction. Here's your entire starter vocabulary. MOV moves data between registers in memory. Add and subdo arithmetic, and they store the result back in the first operand. CMP compares two values by subtracting them internally and throwing the result away. It only sets flags. Right after CMP, you'll almost always see a jump instruction starting with J, G, jump if equal, gene, jump if not equal, JG, jump if greater, JL, jump if less. Those flags CMP set are exactly what the jump checks. Call jumps into another function and remembers where to come back to. Ret returns to that saved location. And push and pop move data on and off the stack. Push writes and moves the stack pointer down. Pop reads and moves it back up. Function calls almost always follow the same ritual at the start. Push RBP to save the caller's base pointer, then MOV RBP, RSP to set up a new base pointer for this function's variables. That two-line pattern is called the function prologue, and once you recognize it, you'll spot the start of every function in any disassembly instantly. Let's put it all together. Say we compiled this tiny C function, int add, taking A and B, that returns a plus B. Disassembled, it looks roughly like this. Push RBP, MOV RBP, RSP, That's the prologue we just learned. Then 2 lines copying the function's incoming arguments, which arrive in registers EDI and ESI by convention, into local stack slots. Then MOV-EX, loading the first argument into EX. Then add EX, adding the second argument straight into EX. Now EX holds the sum, and by convention, the return value of the function always comes back in EX. Finally, pop RBP restores the caller's base pointer, and ret jumps back to wherever this function was called from. Read it out loud in plain English, and it's just save the old frame, stash the 2 inputs, load one, add the other, return the total. Nothing scary about it all. So next time you see a wall of disassembly, find the prologue to spot where a function starts, track what's moving into which registers, remember that EX, AX, and AL are just slices of the same racks, and read every CMP followed by a jump as one connected if statement. That's really it. That's the whole trick. Pattern recognition over 20 or so repeating instructions. If you want to try this yourself, compile any small C file with GCC-S to see the assembly straight from the compiler, or run objdump-d-M intel on a compiled binary to disassemble it. Next video.